Okay, good morning. Let me start by thanking the organizers for the invitation to this beautiful and unique place. We will switch topics again, so I will talk about plasmonics, and then in later parts also a little bit about phonon, excitations of ionic phonon systems. And a few slides of motivation. We already heard a lot about the diffraction limit of light, whether it's fundamental or not. Essentially, the diffraction limit of light tells us that we cannot resolve objects that are closer to each other than approximately half of the wavelengths. But of course, optics always works the other way around. I think this is, there's not much we can do against that. So if one tries to focus a laser beam into some area, essentially we're again suffering from the diffraction limit of light, and we can only squeeze it into a volume with dimensions that again are comparable to the wavelengths of light, which means that light is not really compatible with nanostructures. So these are typically areas of a few microns, and nanostructures are tens to hundreds of nanometers. So there's a kind of length mismatch between optics and nanostructures. And one way to overcome this is to slightly change the rules of the game and to put something in between light and the spot where we would like to focus it. And these are metallic nanoparticles. As probably all of you know, the colors of these stained glass windows are partly due to metallic nanoparticles that are embedded in glass. And depending on the geometry and also size of these nanoparticles, they have resonances at different frequencies, so ranging from orange, red, whatever. And what is shown here, essentially, these excitations are associated with coherent electron charge oscillations at the surface of these plasmonic nanoparticles. So it's a kind of resonance. One is separating the charges, and there is a restoring force. And if we hit the right frequency, essentially, this electron charge oscillation builds up. And this is one part. The second part that is, I would say, evenly important to us is that close to these metallic nanoparticles, there are very strong evanescent fields. So the enhancement of the electric field, because it's kind of a resonance behavior, we shake up this electron cloud, and at the end we really have very strong fields, and we can get field enhancements of the order of hundreds to thousands. So the idea is, so this is the basic principle, we come in with a far field radiation, we have these metallic nanoparticles in between, and if we want to deliver the photon energy or the light energy at a certain spot, we get really very localized fields due to this resonance behavior and the evanescent fields of these metallic nanoparticles. And of course, it also works the other way around. So optics is always working in both directions. If we have a quantum emitter that emits light very weakly, we can put a metallic nano antenna there. This molecule will shake up these oscillations, and it can do it in a very efficient way because we have these evanescent fields of this nano antenna, and then we can really completely modify the optical properties of these quantum dots, molecules, whatever we put there. So the workhorse of this whole field of plasmonics are surface plasmons. And initially, they were first predicted by Ritchie and later observed in experiment on flat surfaces. So if we have a flat surface, we can have a certain kind of excitation here, a surface plasmon, where we again separate the charges at the surface. And we have something that is propagating with approximately the speed of light. So it's a kind of hybrid excitation. It's half light, half matter. And this wave is really guided at the interface between the metal and the dielectric. And the important thing, again, it's confined there. So if we are looking to the electric fields in the perpendicular direction, we see that they are confined there. So it's really an excitation that is bound to this interface. So we have fields that decay in the dielectric and the decay in the metal, very strongly localized. What I'm interested more are not flat surfaces, but metallic nanoparticles. And the situation in a very naive way is similar to quantum mechanics. If you think about electrons, you know, there's the de Broglie wavelengths. And if we kind of confine these waves as we do in an atom, we get standing waves. And in addition to that, we have a kind of quantization criterion, which means that instead of a whole dispersion for the surface plasmons, we get certain discrete eigenfrequencies and eigenmodes. So again, in a flat surface, we have propagating plasmons. In a particle, we get confined modes. And I will show you that, yeah, we can really also experimentally measure these modes. And the advantage here is one can tailor the resonances by changing the geometry, as you saw before with the stained glass windows. The fields are even more strongly localized, so you can really get extremely high field enhancements. In particular, also in the gap region, if you couple particles, you have very, very strong hotspots in between these particles, and so on and so forth. So it's a very, in a physical sense, simple means to confine light by simply designing, structuring the geometry of these particles. I will be talking a lot about experiments. I'm a theoretician, I should say, and I will spend a few slides on how we describe these particle plasmons. And yeah, the way it goes is we solve Maxwell's equation, and we solve Maxwell's equation in the linear regime. So it looks boring at first. We typically are looking to particles that are composed of one material. So for that reason, we are not discretizing the volume, but we use a kind of boundary element method where we only discretize the interface of these particles. Second step, suppose that we have some kind of excitation of the system, which could be a plane wave, it could be a molecule. Later on, I will show you that we can also use electrons in order to probe these plasmons. So we have an excitation of the system, and the system responds. So this would be the induced electric and magnetic fields, and it's a linear problem. So there's a kind of transmission matrix that relates the incoming fields to the induced fields. And once we have solved this problem, so this is the Maxwell problem that we have to solve by using any kind of Maxwell solver. What we have at the end of the day are really the solutions of our system. So we can compute everything we like. We can compute optical spectra. We can compute near field enhancement and all things that are related to that. And I should mention that, yeah, this has been our main contribution. We have developed a simulation toolbox using this boundary element method that can be downloaded from our website. And we are happy that this has been used by really many people in the field. We can look to the problem in a slightly different perspective, and I think it's useful for what I will be showing you later during this talk. Namely, it's a linear system, so in a sense we can decompose the response into the eigenmodes of the system. And the eigenmodes, of course, make very much sense in a physical sense, because they're really the kind of way we think about surface plasmon, that something is oscillating at the particle of this, at the surface of these particles. And as I told you before, this is the problem we are solving. So we have the external fields, we have the incoming we have the induced fields, and we have this transmission matrix. So what we can do in principle is we can seek for the eigenmodes without a specific excitation. So these are really the intrinsic properties of the system. And it turns out that this works extremely well, and it can be done in a very easy way in the so-called quasistatic regime. So when the particle is small, when we neglect retardation effects, we can essentially reduce it to a kind of electrostatic problem with the only difference that we're using the frequency-dependent permittivities. So this works for small particles. I will tell you in a moment what we do for larger particles. For these small particles where we have these quasistatic eigenmodes, it turns out that this transmission matrix can be separated into two parts. One that only depends on the material properties. So this essentially depends only on the dielectric functions of the material. And the second contribution, which essentially only depends on geometry. And this is a nice thing, because we can now look for the eigenmodes of this part here, of the geometry essentially. And we get eigenmodes as we would expect them. Like here with the disk, we would have two dipole modes that oscillate like this and like that. or we have quadrupole modes, and so on and so forth. So a whole zoo of different eigenmodes of these systems. And of course, if we look to other structures like nanorods, this also looks familiar and like really the way we would like to have them for these plasmonic nanoparticles. However, if one is interested in the eigenmodes of the full Maxwell's equation, it turns out that things are more complicated, and this is still quite active research fields of how to do that. There are different approaches, and it turns out that the concept of an eigenmode is not as clearly defined as one would wish. There are different ways. So either you take the transmission matrix for a given frequency and again look for the eigenmodes. This is something we can also do for the Maxwell's equation. Unfortunately, this matrix no longer separates into geometry and material properties, which means that in principle you have to compute eigenmodes for different excitation frequencies, which is not always convenient. There is a different approach that there's now quite a lot of work, namely to seek for complex eigenmodes, which means that we are really seeking for the poles in the complex plane, which means that we get frequencies that have a real and imaginary part. Obviously, the real part is the resonance frequency, and the imaginary part is the damping. And it turns out that this can be done in principle in a systematic way, such that one can solve the problem and really first computes the eigenmodes, and from the eigenmodes you can essentially get the complete response of the system for any kind of excitation. I will not go into it. There are some recipes in the literature that sometimes work, sometimes don't work perfectly, but in principle, so this is work that we have done recently, the mode decomposition works extremely well. So this would be for a small particle, typically you have one, or this would be 3 degenerate modes that describe the whole spectrum. If you go for larger particles, this would be the traditional approach, the blue one. So you see it starts to fail for larger particles. But if you improve things a little bit, it really turns out that there is a very nice agreement between the full simulation results and those where you take into account the right eigenmodes. So I'm not going very much into it, but the main message here is you can take these plasmonic particles here, you can look to the eigenmodes, and they are both useful for the interpretation of your results, but also if you want to speed up calculations. Okay, having said that, this essentially has been the theory part. Now I will show you results that from our collaborations with experimental groups. And I would like to show you in particular that we can use an electron microscope in order to map out these plasmonic fields. And of course, there's a simple reason. We have these strongly confined electromagnetic fields, so we cannot use optics. It's the diffraction limit of light forbids us to use optics. We would not see any kind of spatial resolution there. But what we can do is we can kind of change the probe from a plane wave to an electron beam. And the electron beams can be very localized, so on the order of sub-nanometers. And we can use this electron beam to map out the plasmon fields. And this is how it goes. So this is it. You need a transmission electron microscope. So this is the expensive part. So it's not something you can do very easily. But if you have a TEM with some additional equipment, it turns out to be a beautiful technique. So in principle, the way it goes is you have a very fast electron, typical acceleration voltages would be 200 kilo electron volt, which means that one accelerates the electron to something like 70% of the speed of light. So these are very fast electrons. You send the electrons close or through your sample, through your metallic nanoparticles. And you have a certain chance to excite one of these particle plasmons. I've shown you before that you have many of these particle plasmons. And once you excite one of the plasmons, essentially the electron loses a tiny fraction of its kinetic energy. So 200 kilo electron volt, it typically loses 1 or 2 electron volt. So what you have to do at the end is you have to spectrally deconvolve the loss of the electron, and then essentially also by raster scanning over the sample, you get spatial resolution and energy resolution of your particle plasmon fields. Critical thing, of course, is you need a beam that is spectrally quite narrow, so 200 kiloelectron volt. It should typically have a full width of half maximum of about, let's say, 0.2 electron volt. This is a typical thing, such that you can really resolve these different excitations here. Okay, essentially, EELS, so electron energy loss spectroscopy EELS, was used to first observe surface plasmons. You know that you cannot directly excite them optically. You need some tricks, which are this Otto-Rether geometry, Kretschmann-Rether geometry. And this is, I think, this original paper of Powell and Swan, where they sent an electron beam through a thin layer of aluminum at that time. Then you see the bulk plasmon, which is this longitudinal excitation inside the electron gas. And on the low energy side, an additional peak appears, which is due to the surface plasmon. So I think this was the first observation of the surface plasmons. It turns out that this technique is evenly, or is probably more powerful, if you're looking to metallic nanoparticles. So this is the first experiment where I was involved. What is shown here is a gold nanorod sitting on a kind of support. This is a carbon grid at this here. And then you see here that the electron beam is raster scanned along this nanorod here. This is the spectrum. So here we spectrally resolve the different loss energies. First thing I would like to show you, this is the zero loss peak. So this is essentially, it's not, the electrons not just have one energy, they have a kind of energy spread. So this is what limits the resolution of EELS. And then you see there are certain loss energies. There's a peak here where now you see nothing at the moment, but now this peak shows up again, right? So you have one peak at low energy that depends very much on the position of this electron beam. And then you also see the other peaks which are associated with the dipolar mode, as I will show you in a moment, and the higher order modes. So if you now raster scan over the sample, in this case it was a slightly different experiment, but I'm not going into the details. Essentially you get a beautiful picture. This is really an experimental picture of the fields. It's not trivial to say what one is really measuring, so we can discuss afterwards what it really is. But at least what we really see here are the dipole fields. Yeah, so it is not sensitive to the polarity, so for that reason you only see the absolute magnitude of the field. But this is really how you would expect for a rod plus minus, which is oscillating back and forth. The other peak would be a quadrupolar peak, so it's a high excitation of this rod mode. Okay, so how far can we push this thing? What we have done recently is a collaboration with the group of Ferdinand Hofer and Georg Haberfellner at the Technical University of Graz. And what they were able to is to measure both EELS. And in addition to that, they also made tomography where they can really map out the 3D shape of these metallic nanoparticles. So this would be, in this case, we have silver nanorods. Two silver nanorods that are coupled, and essentially by tilting the sample and doing back-filtered projection, you can really get a complete 3D geometry of these samples. And what we are essentially doing is we take really this geometry as it comes out from experiment. We put it into our Maxwell solver, and we compare the experimental results with the theoretical results. And it turns out that it works almost too good. So first thing you realize, of course, there's more broadening here, which is due to this convolution, so the limited resolution of EELS. If you look very carefully, you will realize that there are also some differences between of the energetic position of the peaks, which is probably also due to the fact that we use some simple data for the dielectric function. So we use data taken from optical experiments. One could try to optimize a little bit these permittivities. On the other hand, if you really look to the EELS maps, let's put them all on, you start to realize that this is working extremely well. So let's go to a mode like that. So this would be two coupled quadrupole modes that you see here. And because they are not perfect, you will see that, for instance, this is shifted a little bit towards the corner. And you will see essentially really the same behavior in both the simulation and the experiment, which shows you Maxwell's equations are powerful, and plasmonics is essentially a game where you play with Maxwell's equation, and if you do things right, if you have the right input information, it works. So the agreement is really almost perfect between experiment and simulation. Okay, so we started to think whether one could go further, and if you go back, if you look to these Eels maps, essentially what you're measuring is something like the electron is penetrating along this direction, so it moves along this direction, and it's interacting with the fields of these plasmons along this direction. So essentially you see the fields projected along the propagation direction of the electron. In principle, it's even a little bit more complicated because the electron is doing two things. First of all, it's exciting this particle plasmon, and then it performs work against the particle plasmon. So for that reason, it's not a local interaction, but it's a non-local interaction, which makes the analysis a little bit complicated. I skipped the details, but in principle, there were two papers back in 2013. One was a theoretical paper by our group, and then done independently, so this was not relying on us. There was a very beautiful experiment by the Mitchley group in Cambridge, where they were investigating a silver nanocube. So you have this nanocube, and what they did now is really to tilt the sample. So these are the different tilt angles. And under different tilt angles, you integrate essentially the electric field along different directions. And then using the model with the quasistatic, so this quasistatic model, they did some kind of reconstruction of the plasmonic fields. And they observed something that I think is very beautiful. On the one hand, so you get the different modes. So this would be the low energy mode, where essentially it's a question of dimensionality if you look here. So the low energy modes are confined at the corners of this cube. The next modes at the edges of the mode, and then you have the phase modes. And because it's sitting on a substrate, this is a silicon nitride substrate, typically with a thickness of 20 nanometers. And silicon nitride has a very high permittivity of about 4. For that reason, essentially the electromagnetic fields of the lowest mode are confined at the lower interface between the silicon nitride and the silver, and with slightly higher energy at the upper mode. If you go into details, it turns out that it's very unclear what you really see here. So the theoretical support, they gave a theoretical support which is kind of fine. We did the same thing. But it turns out that this is very complicated to generalize this to other structures. So we have worked for a while on generalizing it, in particular for the full Maxwell's equation. And without going into detail, we are using now, so the idea is we're using these eigenmodes I was telling you before. So we take the 3D geometry, we use the eigenmodes as a kind of generic basis. And then we are trying, so this is our basis where we assume that this is representing the response of the system. We put in some coefficients, and now we are trying to optimize the coefficients. So to give you an idea, it's something similar to, you know, that you can decompose any electromagnetic field into vector spherical harmonics. So it's a complete basis. And essentially, we're using here a more educated guess for these eigenstates, but otherwise this is also again a complete basis. So if we choose the right coefficients here, in principle we should be able to match the experimental results. And this is what we do in our approach. Essentially we have the experimental Eels maps for different tilt angles. We can do the same thing in theory, so essentially we integrate just the electric field along the propagation direction of the electron. And now we are kind of optimizing these coefficients in such a way that the experimental and simulation results come as close as possible to each other. So it's an inverse problem that we are solving here with some pre-information that we put into our system, but still we can do it. And yeah, so once we have got the best coefficients, essentially we have solved, we know the photonic environment of the system. So I would say it's a mainly an experimental technique with some theoretical input. The theoretical input is providing the basis and the coefficients, so how these different modes contribute to the electromagnetic response are sitting here. And I just show you the results because I like them. They are beautiful. They give us a feeling of really the 3D electromagnetic fields. So once we have computed this Dirac-Green's function, we know everything about the system. What I'm showing on the next slides is this photonic local density of states, which the photonic local density of states, you can think of a quantum emitter. If you have a dipole with a dipole moment, and you place it at different positions, yeah, you will see that they couple strongly or weakly to the photonic environment. So the color now depends on how strongly it couples to the photon fields, and the direction indicates in which direction a dipole would couple strongest, right? So this is what we are plotting here, because it's a, as you see here, it depends on 6 coordinates, and in addition it's a tensor, so it's a very complicated object. And yeah, this is the particle that we are using, which results from electron beam lithography. It's not a very beautiful structure, so if you Martin, you would probably not be very happy with something like that. But we were, because there is this kind of artifact from the lift-off process, so this thing here, and which turned out to be a beautiful thing, because if you now look to the eigenmodes, the lowest one is really confined at this needle here. Yeah, you see that you have this very localized mode at this protrusion of the particle. The next mode would be a dipolar mode, where you have the 2 dipoles oscillating in phase. So you have a strong, this hotspot in between. If you look carefully, you also see, so these are just different views of the same mode. Yeah? You see there's a kind of hybridization. So this particle also acquires some oscillator strengths from the dipole mode. And then you also see other modes, like dipoles oscillating like that. And you also see the antibonding mode, so where the electromagnetic fields move like that. So you have the equal charges in the middle, and if you look to the field lines, they really go like that. Yeah? So it's a beautiful technique that really works also in experiment, if you want to look to the 3-dimensional electromagnetic fields. And you can also look to different structures, like vertical coupling. So in this case, we had 2 vertically coupled triangles. And again, looking to the tilted maps, you don't see that much what is going on. You put it into this machinery that is reconstructing the fields. And if we do that, you nicely can distinguish the bonding mode, where you have opposite charges on the 2 triangles, from the antibonding mode, where the charges are the same. So for that reason, there are weak fields in the gap region versus strong fields in the gap region. Okay, the last part of the talk, I will show you new results that go from plasmonic nanoparticles now to ionic systems. And the system, or the reason why we have been interested in that, is the improvement in electron microscopy. So this is the typical electron beam I showed you before, with a full width of half maximum of 250 milli-electron volt. There's a new generation of electron microscopes, the neon microscopes, that have here, so it goes the other way around. So here it goes up, and here you have the spectrometer. And what is new here is really the monochromator. So the monochromator is working in a different way, and you get extremely high spatial energy resolution, as you see here. So this is the zero loss peak, and you can really, by designing this monochromator, which is a very difficult thing, but in principle you can get spectral resolution of the order of 9 milli-electron volt. This is a collaboration with Maureen Lagos and Phil Batson from Rutgers University. And you see they are pushing hard over the years. They start with 10 and they go down to 6.5. And if you go down to really a few milli-electron volt, you can map other things, like the ionic vibrations of an ionic crystal. I will show you the system in a moment. So we're looking to magnesium oxide tube, which has really this simple rock salt structure. So if you compare, for a metal we have here, this would be a Drude dielectric function. And for an ionic system, we would have a Drude-Lorentz dielectric function. They look very similar. Here we have a kind of resonance frequency. Here there is no, there's no frequency like that. But in principle, the main difference is that for metallic systems, the excitations are in the visible range. This is because electrons are much lighter than the ions. And because the ions are so much heavier than the electrons, for the ionic systems, we see more or less the same modes I showed you before. But the difference is that they are shifted to the infrared regime. Yeah, so it's a different system, but you see very similar effects. And I will show you a few results now. So again, it's a cube. And you will see the results are really similar to what I showed you before from the experiments of this Midgley group. So this is the magnesium oxide cube that is sitting on a carbon grid. And we will see in a moment experiments where the electron beam essentially is raster scanned over the specimen here. Yeah, as a theoretician, of course, it's always interesting how you make these samples. In this case, it turns out that it's very simple. You take magnesium, you burn it, and then you have your carbon grid, and with the carbon grid, essentially, you try to get the structures that are formed automatically. And it seems that depending on the humidity, you either get cubes, and later in the year, when it becomes humid, you predominantly get spheres. So it's something that depends a little bit on luck and on the conditions that you have. Okay, so this is the experiment, and again, really the great thing about it is this highly increased spectral resolution. The red one now is showing you the electron beam without the specimen. So this would be really this great spatial energy resolution of 10 MeV. And then you see if the electron beam passes by, for instance, a phase, as shown here, you see that there is, at a certain frequency, you have a higher probability of losing energy, which means that here the electron is exciting a phase mode. It's not a plasmonic mode, but it's an ionic mode. And you also see if you move towards the edges at the lower energy, you really see this additional peak here. What is also nice, if you look to the anti-Stokes sides, in principle, this is the energy gain regime. You also see some features here. So this is a really unprocessed data. Even with the naked eye, you see that something is here. And the reason why it's here is because they are thermally populated, which means you have a thermal vibration of the system. The electron comes by, it picks up a phonon. So energy is transferred from the cube to the electron. And in principle, with that, you can map out the thermal near fields. So you should find, and you also find a ratio of n to n plus 1. So this is what is essentially shown here. And the third thing I would like to emphasize, and this was really the part that, so this is the exciting part, but this is the part that is also interesting. If the electron beam goes through the cube, you see they have a lot of structure here, and I will say a few words about this in a moment. Okay, so this is now the experiment. Again, this is the region that was raster scanned with the electron beam. Let's go through it. Yeah, you see at lower energies, these are modes that are just here. You go up in energy. At some point, you should see the phase mode, the edge mode, and then at the higher energy, the phase mode. So if you, again, look to the experimental results and also to the simulation results, similar to the plasmonic case, but now at a much lower energy, you find that you have modes that are confined to the edges of the cube or to the face of the cube. And again, this is showing you that this is also in nice agreement with the simulation results. What took us a longer time is to figure out what is going on if the electron beam goes goes from the aloof geometry to the penetrating geometry. What you see is the spectrum is completely changing once you enter the cube, and you also see at close to the interface, still things are happening, and then you get a kind of constant structure with I think it's obvious what it should be. Essentially, one is exciting the whole phonon spectrum of your cube. So this method, in principle, gives you a technique in order to map out phonons in a nanosystem with very high spatial resolution and energy resolution. And of course, the spatial resolution is interesting if you would like to look to something like an interface or a defect of the system. Okay, we tried to model this. We used a simple molecular dynamic simulation. Why not? So this is again the same thing. So this would be the electron beam raster scanned over a very small, so this is something like 3 nanometer cube. You see that it lights up at the positions where the ions are sitting. It's a kind of classical simulation. So you see if you change now in energy, go up in energy, they light up here in this case. And then at certain energies, you see that you get modes that extend into the exterior, which would correspond to the surface plasmon modes, but here this would correspond to surface polariton modes. Okay, so these are the typical modes. Inside the structure, one has to come close to the ions in order to excite the phonon mode, but then you see a bunch of different modes, like edge modes, phase modes. You see localized LO modes that are really localized just to the interface. And then you also see the confined LO corresponding to the bulk plasmon, if you like, if you want to take this comparison. Okay, and then you can look to different simulations, molecular dynamics, lattice dynamics. I'm skipping that. You can decompose it really in terms of the phonon modes that are inside the system. And you see that it's particular, of course, the LO modes, the long-range modes to which it contributes. But when you come close to these atom columns, essentially you can excite a whole bunch of, yeah, I'm done, I think, yeah. Of different modes. Okay, so as the chairman already is indicating, I ran out of time. So it was really my last slide. I would like to thank the collaborators. Andy Trögler, long-standing, so he's one of the backbones of my group. The group of Ferdinand Hofer doing electron microscopy, Joachim Grenn, who is doing nano-optics and producing these structures. And I also showed you a lot about this collaboration with the Rutgers group of Phil Batson. Thank you.